So this is an example that to me kind of serves as a universal example for the whole module. That if you're able to navigate your way through a problem of this type, then it means that you are a Module 9 master. You've gotten everything that you could possibly need to get out of this. This is the hardest kind of problem that we'll do. But it begins in the same way as the last problem that we just did, asking us to add together these two rational expressions. And so our sensibilities are still the same. We should always, anytime adding fractions was the first thing that you should come to your mind to worry about. Right, because we need common denominators. And so we'd like to, if possible, common denominators, there we go. To the extent that it's possible, we'd like to find denominators that can put both of these fractions on a common footing. And then bring both these fractions into terms of those denominators and then add them together. And of course, the degree of difficulty here is that both of our denominators are nasty. They're both quadratic polynomials. And so before we can go forward, let's take as our first step. So we did this last in our previous example, but it's a good idea in problems like this to do it first. Factor everything in sight. Because once we've factored everything in sight, we can kind of see whether or not there's something that's already in common to these two quadratics, or whether they have nothing in common and we need to multiply across. So what that means is that I want to take each of these denominators, 4x squared plus 17x plus 15, and also 4x squared minus 11x minus 20, and I want to factor each of them to get us started. And in each of those cases, because we have a quadratic trinomial, what's the strategy that we should be thinking about for how to factor something like 4x squared minus 11x minus 20? So to factor this, because the leading coefficient in this quadratic is not 1, we should use the AC method, which has us searching for a pair of numbers which multiply together to give me a times c, and in this example, a is 4, c is negative 20. And so the AC in my AC method is negative 80. Negative 80. So the product needs to be negative 80, and the sum needs to be negative 11. A pair of factors which are going to get me to 80 are 16 and 5. We need them to have opposite signs, and we need their sum to be negative. Therefore, we need the bigger of the two. Yeah, negative 16 and positive 5. And so, again, what we do with that is we use that to split the middle term. 16x plus 5x. Yeah. And so if we're doing this via factoring by grouping, now we have it set up in a way that will allow us to factor the first pair of terms and factor the second pair of terms, and for those factorizations to have a factor in common. So from 4x squared minus 16x, what common factor can I pull out? 4x. And between 5x and negative 20, what common factor can I pull out? 5. Okay. And then what's left over if I factor 4x out of 4x squared minus 16x? And when I factor 5 out of 5x minus 20? There's our common factor, x minus 4. So that when I factor this by grouping, 4x plus 5 times x minus 4. There we go. We're understanding our original denominator in a different way. We're understanding it in its factored form. We'll do the same thing for our second denominator. Using the AC method on this one splits our middle term into a 12 and a 5, 12x and a 5x, 4x squared plus 12x plus 5x plus 15. And when I factor that by grouping, I again can pull a 4x out of the first pair of terms. I can pull a 5 out of the second pair of terms. And in both cases, the cofactor that remains is x plus 3. So, at the end of the day, this factors as 4x plus 5 times x plus 3. And there's something a little bit reassuring about this, because now looking at my original two fractions in this new way, what do you notice that might actually help us? the 4x plus 5 is a common factor in both denominators. So we can use that. Now that I've factored everything, I find that I don't have to, I'm not stuck with all 4 of these factors multiplied together as my new common denominator. Instead, what common denominator can I shoot for in this example? I already have a 4x plus 5 in both of my denominators, so I don't have to have it twice, I guess is the moral of the story. I do need the x minus 4 because it's a factor in the first denominator, and I do need an x plus 3 because it's a factor in the second denominator. But I need each of those, again, only once. So my common denominator that I can use just takes the minimal set of common factors among the denominators of the factors that we originally had, factors of the denominators that we originally had. And we're going to use that as our common denominator for both of these. 4x plus 5, x minus 4, x plus 3. So each factor appearing only once. And now the question is, how do we find the numerators? Yeah, so if we were doing this the same way we did the last problem, we would multiply the numerator of the first by the denominator of the second. The problem with that is that we've already accounted for the 4x plus 5 in my first fraction. So I shouldn't multiply by 4x plus 5 again in my second fraction. So when I do my cross multiplication, I want to cross multiply only by new factors. In other words, here's what I mean.
4x plus 5 is going to remain.
Right, 4x plus 5 I don't need to multiply by because I already had it. So I only need the x plus 3 from the second one. That's my new factor. So another way to see it is when I write the 6 here and the x plus 3 here. What you'll notice is that this is just my original. And when I tack an x plus 3 in the denominator, I only needed one x plus 3 in the numerator to balance it out. If I added another 4x plus 5 up top, I would now have too many 4x plus 5s. And the 4x plus 5s, if we canceled them, we would go backwards to a different starting point than we started. But if I take these x plus 3s, which are common factors up and down, and I cancel them, I do, in fact, get back to the original rational expression that I started with. So when you cross-multiply, only cross-multiply by things that are new to the numerator that you're multiplying. So when I multiply the 6, I'm going to multiply it by x plus 3 only, and not by also 4x plus 5. Put another way, what did we do to get from this first fraction to the first fraction after the equal sign? What's the difference between the denominators? We combined right, and more specifically, the difference between those two denominators is that we've multiplied by what? What's missing in the first denominator but present in the second one? X plus 3. And only x plus 3. Which is why when I multiply the numerators to balance them out, I'm again just going to multiply by x plus 3. Right? So that's thinking about it the way that we thought about fractions when we were adding them long ago when they were just numbers, right? Just multiply by whatever you multiplied by in the denominator, multiply by that same thing in the numerator. And so my shorthand for that is just cross-multiply by the new factors, but maybe this is a better way to think about it if you are remembering how we did it with fractions in a different way than that. In either case, in the first fraction, I multiply top and bottom by x plus 3. And in the second fraction, what should I multiply the 2 by? X minus 4, just the new factor, because we already have the 4x plus 5. And so I'll have my 2, and then I'll have an x minus 4. And again, a consistency check on yourself is that if we were to cancel out the common factors on the right, the x plus 3s would go away, we'd be exactly back where we started, and the x minus 4s would go away in this one, and we'd be exactly where we started. Right? So you can always check your work as you grow these rational expressions to have bigger denominators, just by checking to make sure that if you were to do the cancellation, and go backwards, you would in fact end up where you started. This is far and away, I think, the most challenging part of the process of adding these two together, is figuring out what do I need to multiply by in order to balance these two. Because now that we've done the hard work of finding that common denominator, so now common denominators kind of become step 2 instead of step 1. But now the denominators are common, we can continue just by adding across the numerators. Well, so now is where we have to be a little careful. So let me write this addition just by combining these two together and writing the denominator only once. Right? So that's what we would get if we add across. I'm going to put the plus sign back in here. But now we have to add this expression in the numerator carefully, right? Because they're not quite like terms. One of them has a factor of x plus 3, the other has a factor of x minus 4. So some care is needed here when we simplify this numerator. In fact, if I wanted to simplify this numerator, what should I do with 6 times x plus 3? Yeah, I'm going to want to get rid of the parentheses by distributing the 6 and distributing the 2. And so this is the point in the process where we do want to distribute multiplication. This is, in fact, the only part of the process when we prefer to do the opposite of factoring. Right? Because distributing multiplication over addition is the opposite of what we're doing when we're factoring. So that what I'll end up with here is 6x plus 18 plus 2x minus 8. And then my denominator is still the same denominator that we had over here. 4x plus 5, x minus 4, x plus 3. But now that I've gotten rid of my parentheses, now I do have like terms that I can combine with one another. 6x plus 2x giving me 8x, and 18 minus 8, 10. So I'll have 8x plus 10 up here on top. Now we've done the addition, we've done the simplifying in the numerator. Now the only question that's left for us is, can we simplify? Can we reduce into lower terms? In other words, can we cancel anything? What do you think?
Yeah, 4x plus 5.
4x plus 5. Okay, how do we know we can cancel 4x plus 5? Yeah, exactly. We can't cancel until we factor. And so we look in that numerator and say, how do I factor 8x plus 10? What do those two terms have in common?
No.
Close. They have a 2 in common. And so when I factor a 2 out of them, I get what's left, 4x plus 5. And sure enough, this problem was really set up in a nifty way, that even at the end of all of this work, we end up with a factor we can still cancel from the numerator and denominator because it's in common. We had a factor of 4x plus 5 upstairs, and we have a factor of 4x plus 5 downstairs. And only when we have a common factor upstairs and downstairs can we cancel that common factor and get us to our final answer. 2 over x minus 4, x plus 3. And at which point I would recommend just leaving it there. We could refoil the denominator back out and get x squared minus x plus, or minus 12, rather, downstairs. But at this point, I think we have to rest on our laurels because we've done a lot of hard work, and that last step is optional. So again, the role of factoring is always our mantra every time, and every step of the game, with the exception of adding these two numerators together. That's when it was more convenient for us to anti-factor, to distribute multiplication over addition, get rid of parentheses. But factoring is a great first step, and it's also an essential last step. Because we don't know what we can cancel. We don't know what we can make simpler until we know what the factors are. And also, we didn't know how to make a simple common denominator until we knew what the factors of our original denominators were. But once we knew what those original factors were, we could make a common denominator that was simpler than it otherwise would have been. And once we knew what the common factors were in our final answer, we knew that we could get rid of a 4x plus 5. That's the only way to know. And so when people screw up in working with rational expressions, it's usually because you didn't factor at first. So always be factoring. A, B, F. I wish it started with C. Always be factoring when working with rational expressions, because it's the only way to know for sure whether we can simplify.